Long before science had equations, telescopes, or particle accelerators, human civilizations were already asking the same question. How did everything begin? The ancient Greeks spoke of chaos, a formless state from which order emerged. In Indian philosophy, the universe was born from a primordial vibration, a sound that preceded matter itself. Biblical texts opened with a simple but radical idea, in the beginning, implying that the universe had a starting point, not an eternal past. Across cultures separated by time and geography, one intuition kept returning. The universe was not always as it is now. It began in a radically different state, hotter, denser, less structured, closer to pure energy than to the world we recognize. Modern cosmology approaches this ancient intuition with mathematics instead of myth. When people hear the term Big Bang, they often imagine a colossal explosion erupting into empty space. But the reality is far stranger and far less cinematic. The Big Bang was not an explosion at all, but the rapid expansion of space itself. In its earliest moments, the universe was unimaginably hot and dense, filled with energy rather than familiar matter, and opaque to light. There were no galaxies, no atoms, and no clear separation between space and time as we experience them today. Because no telescope can directly observe this primordial era, scientists reconstruct it indirectly by measuring how the universe expands now. By detecting ancient radiation that still permeates all of space, and by identifying the precise points where our physical laws begin to break down. As we follow these clues backward toward the beginning, the question of what the universe looked like becomes something deeper. It is no longer a search for an image of creation, but a journey to the very edge of human knowledge, where science, philosophy, and our oldest questions quietly meet. So when we follow those clues backward, we do not arrive at a scene we can watch, but at an idea that quietly refuses to be filmed. Most people, when they hear the words Big Bang, see something simple and vivid: a dark, empty space, a tiny point of light. Then, suddenly, an enormous blast, matter flying outward, waves of fire, fragments of future galaxies spinning away from a central wound in the darkness. It feels intuitive. It feels like how big things usually begin in our stories. With an impact, with a blast, with a before and an after that are easy to separate. But if we take that picture seriously, and we hold it up next to what modern cosmology is actually saying, it starts to fall apart in our hands. For that picture to be right, space would have to be a kind of pre-existing stage, a vast black room, waiting there in silence, into which the universe suddenly explodes. There would be a center where the explosion started. There would be an edge where the debris has not yet reached. And somewhere, if we push the fantasy far enough, there might even be an outside, a vantage point where you could sit and watch the whole thing unfold. That is not what the Big Bang describes. The Big Bang is not an explosion in space. It is the expansion of space. The distances between things grow, not because they are all flying away from some central blast point, but because the geometry that measures those distances is changing. It is as if the ruler itself were stretching, everywhere, all at once. There is no central point where it happened. Pick any galaxy. From that galaxy's perspective, all the others seem to be receding. Pick another one. The same pattern appears. Every place can call itself the center only because there is no preferred center at all. The expansion does not push galaxies through space like shrapnel through air. It pulls space itself wider, carrying the galaxies with it. We sometimes borrow an image to help. Imagine dots on the surface of a balloon. As you inflate the balloon, Every dot moves away from every other dot. None of them are sitting at the special point where the expansion began. There is no edge on the surface itself. The expansion is not happening in the surface. The surface is what is expanding. Even this is only an approximation. A thin skin of rubber is still an object in some larger space. Our universe, as far as we can tell, does not need that extra room. The expansion does not require a surrounding void. It is not pushing into anything. It is simply changing its own scale. Once you let that sink in, the question, where did the Big Bang happen, starts to sound different. Hidden inside it is an assumption that space was already there, like a quiet hallway waiting to be filled with noise. But the Big Bang is the story of that hallway itself coming into being, of distance and direction and duration taking on meaning at all. Asking for the address of the origin is like asking, very seriously, what is north of the North Pole? We can push this discomfort a little further. When we ask, what did it look like right after it began? We are reaching for a mental picture. We want a view. We imagine a camera pointed at the newborn universe. Maybe we imagine ourselves standing at some safe distance, watching. But there was no safe distance. There was no outside ledge to stand on. There was no surrounding darkness, waiting patiently while a bright speck grew inside it. There was only the universe, hot, dense, young in a way that our words barely touch. And whatever it looked like, there was no external eye to see it. So instead of asking what it looked like, cosmology quietly changes the question. It asks what the conditions were, not the image, but the state. How hot was the early universe? How tightly packed its contents were? How smooth or lumpy? Whether light could travel freely or was constantly scattered? Whether matter existed as the kind of atoms we are made of, or only as more primitive ingredients? This shift matters, because in those first moments, the universe was not transparent the way it is now. Light could not simply sail through space in long, clean paths. It was absorbed, emitted, scattered, tangled in a storm of interactions. Talking about what things looked like becomes slippery when light itself could not carry a stable picture very far. So we trade images for descriptions. Instead of saying, "It looked like a fireball," we say, "It was filled with an incredibly hot, dense mix of radiation and particles, all interacting constantly." Instead of saying, "I can imagine it," we say, "I can state what kind of physics seems to have been in control." I was no there, Fiona. The word space-time appears here, and it can sound abstract, but it is just a way of admitting that space and time are not separate ingredients. They are woven together into a single fabric of relations. Where you are and when you are belong to the same structure. When the universe expands, it is not only that distances change. The way events line up in time and space also shifts. The rules that tell us how far apart two moments are, or how long light takes to cross a region, are part of that fabric. The Big Bang model says that if we follow those rules backward, we find that fabric becoming more and more tightly wound. The distances between things shrink. The temperature climbs. The matter we know cannot hold its form. Atoms fall apart into smaller pieces. And even those pieces, under extreme conditions, may not behave as separate, familiar particles. At some stage, our current theories are still comfortable. We can write down the laws that describe how a hot plasma behaves, how radiation and matter interact, how expansion cools things over time. Those laws have been checked in laboratories and in the sky. They fit the evidence well, but as we keep pushing backward, we reach a threshold where that comfort fades. The densities and energies we are talking about grow so extreme that gravity and quantum effects can no longer ignore each other. The very idea of a smooth fabric of space-time begins to wobble. Our usual equations, which work so beautifully for stars and galaxies and planetary orbits, start giving nonsensical answers. This is why cosmologists are careful. When they use the phrase Big Bang, they do not mean the very first instant of existence in a clean, settled sense. They mean the hot, dense, early phase from which the observable universe emerged, described up to the point where their tools still make sense. Beyond that, language becomes fragile. So when you picture the origin as a ball of fire expanding into darkness, you are doing something deeply human. You are borrowing from explosions, from storms, from sunsets and camera zooms. You are using the vocabulary of surfaces and objects and horizons that your eyes evolved to handle. The universe is asking you to give that up. It is asking you to imagine an event that is not inside space, but of space. A beginning that does not unfold in time, the way a movie reel does. But that brings time itself into being as part of the story. An expansion that has no center and no edge. Only a change in the scale of everything. We are not built for that. Our nervous systems evolved to navigate rivers and forests and rooms, not the birth of space-time. So it is not a failure of imagination to find this difficult. It is a clue. A reminder that our most natural picture of the Big Bang is not simply incomplete, but misleading. If we are going to ask what the universe was like right after it began, we have to start by letting that old picture go. We have to accept that what it looked like is the wrong kind of question, or at least a question that must be translated into something colder, more abstract, and strangely more honest. From here on, the story of the beginning is not a scene we replay in our heads. It is a reconstruction from traces, a careful inference from what survived. And already, at this first step, we can feel something important shifting. The universe is not a distant spectacle we watch explode. It is the condition that makes watching possible at all. If the universe is not a fireworks show we watch from the outside, then someone, at some point, had to be willing to treat it as something stranger than a spectacle, as a system that could be run backward in thought until the very idea of before started to slip. That someone was a quiet Belgian priest who loved equations. Georges Lemaître did not begin with a mystical vision of creation. He began with a set of rules. The rules came from Albert Einstein's theory of general relativity, which is a way of saying that gravity is not an invisible force pulling at things across empty space, but the bending and warping of space and time themselves. A heavy object, in that picture, does not tug on its surroundings. It reshapes the stage on which everything moves. Most people, even many scientists in the early 20th century, were still attached to an older intuition. The universe, as a steady backdrop. Stars might be born and die. Galaxies might move and collide. But the whole should, in some deep sense, remain the same. Eternal, unchanging on the largest scales. Einstein himself tried to encode that comfort into his equations. They naturally allowed for change, for expansion or contraction. To suppress that, he added an extra term, called the cosmological constant. This sounds technical, but it is basically a mathematical adjustment meant to hold the universe in a delicately balanced, static state. Lemaître looked at the same mathematics and refused to lean on that comfort. Cosmology, the study of the universe as a whole rather than of individual stars or planets, was still young as a discipline. Many people saw Einstein's equations as powerful but abstract. Lemaître treated them instead as a practical tool. If they described how space and time behave in the presence of matter and energy, then they should describe the behavior of a universe that is filled, everywhere, with matter and energy. He imagined a cosmos that is roughly the same in all directions, on large scales. No privileged center, no cosmic edge, just matter spread out in a broadly uniform way. Give such a universe Einstein's rules, and you get a surprising conclusion. It cannot sit still. The geometry must either swell or shrink. From there, the step that changed everything is deceptively simple. If the universe is currently expanding, then in the past, it must have been smaller. Keep going, and it becomes smaller still. At some finite earlier time, the distances between things would have been so reduced that the entire observable universe would fit into a region whose density and temperature defy ordinary description. Lemaître called this hypothetical state the primeval atom. The phrase sounds like something from a myth, or like a literal atom of chemistry. It was neither. He did not mean a tiny speck sitting in empty space, waiting to blow apart. He meant a state in which all the contents of the universe were compressed into an unimaginably compact condition, beyond the reach of everyday concept. It was a label for extremity, not a detailed picture. In that sense, the word atom in his phrase is closer to its older meaning, something indivisible, a unity that has not yet split into the diversity we see now. The primeval atom was a way of saying there was a time when all the structure, all the galaxies and stars and planets, all the complexity we live inside, had not yet unfolded. It is important that Lemaître reached this not by desire, but by deduction. He was an ordained priest, but in his scientific work he insisted on a clean separation between theology and physics. He argued repeatedly that the beginning described by his equations had nothing to do with religious doctrine, and that mixing the two would damage both. For him, the universe having a finite past was not a spiritual claim. It was simply what followed if you trusted the mathematics and the observations available at the time. To rewind the universe, in his hands, did not mean pressing a mental replay button on a cosmic movie. There was no film to inspect. It meant taking the current expansion and tracing it backward using the equations that describe how space-time evolves. Space-time is just the joined fabric of space and time together, where and when as a single thing. If you shrink the distances between galaxies according to those rules, you also change the rhythm of time. The way events can be ordered, the speed at which light can cross a given region. Lemaître's calculations showed a universe that, going backward, becomes denser and hotter without limit. This is where another difficult word appears: singularity. In mathematics, a singularity is not so much a real object as a signal that your description has broken down. It is a place where some quantity you are calculating, like density or curvature, shoots off to infinity, and the equation itself stops being trustworthy. When his models reached such a state, Lemaître did not claim he had literally found the first instant of existence. He was more cautious than that. He understood that the singularity might be telling him that new physics was needed. That quantum theory, the framework that governs particles and energy at very small scales, would have to be merged with general relativity to say anything reliable about that extreme beginning. Quantum theory, at its core, says that at very small scales, certainty dissolves into probability. Particles behave like waves, and waves behave like particles. Energies can fluctuate spontaneously for tiny intervals. Lemaître sensed that a universe traced back into such a regime could not be described by smooth, classical pictures. His primeval atom was already a compromise between his equations and his imagination, an attempt to gesture at a quantum birth using the limited language available. Not many people listened at first. His early paper on a universe of increasing radius, which relates the rate at which distant galaxies recede to their distance from us, appeared in a relatively obscure journal. Very few physicists read it. When he personally presented the idea to Einstein, the reaction was famously cool. "Your mathematics is correct." Einstein reportedly said, "But your physics is abominable." Behind that sentence lay more than a technical disagreement. It carried an inertia of worldview. The thought that the universe itself might have a finite age, that it might have emerged from a hot, dense state, felt to many like a retreat toward mythology. A scientific universe, in their minds, ought to be eternal in both directions of time. Lemaître was proposing something more unsettling. The finiteness of the past was not, in his view, an imported myth dressed in symbols. It was the natural implication of taking general relativity seriously on cosmic scales. The universe did not have to be eternal just to be respectable. It had to be whatever the combination of theory and observation insisted it was, even if that meant facing a beginning. There is a fragile, almost quiet audacity in that stance. He was not shouting about creation. He was following a chain of logic to the point where it began to twist on itself. At that edge, he did something rare. He stopped. He acknowledged that beyond the primeval atom, beyond the point where his equations suggested a singularity, his tools were inadequate. There would be no confident story about before IDs. In doing so, he planted the seed of a new attitude toward the origin of the universe. The beginning is not a scene we already know, waiting to be confirmed. It is a boundary that our best ideas push us toward and then fail to cross. The very notion of time since the beginning is a product of the same equations that fail at the limit. Our measure of cosmic age is drawn from a framework that admits, honestly, that it cannot define age at the starting line. But deduction alone is not enough. It is one thing to imagine the universe rewinding into a dense state. It is another to show that it is truly expanding now. For Lemaître's vision to become more than an elegant possibility, there had to be evidence that space is stretching, that galaxies are receding from one another in a way his calculations anticipated. That evidence would not come from philosophy or theology. It would come from light, from the subtle way its wavelengths shift as it travels across the widening fabric of space, from the patient work of measuring how the glow from distant galaxies changes as they slip away. When those observations began to align with the pattern he had predicted, the idea of a finite, expanding universe moved from the margins toward the center of cosmology. But even then, the core of Lemaître's insight remained strangely modest. The universe having a beginning was not a triumphant answer to an ancient riddle. It was a side effect of trying to describe what we see with the tools we have, and admitting where those tools fail. To think about the Big Bang in this spirit is to accept that the idea of a beginning is itself a fragile construct, not a single bright moment at the start of a timeline, but a limit where mathematics breaks, language stumbles, and yet something real is being pointed at. A universe that, when rewound, does not blur into an endless past, but narrows toward a place where our questions about before lose their footing. From that narrowing, from that conceptual cliff where Lemaître chose not to pretend he could see further, another question naturally rises. If the universe really is expanding now, how do we know? What? Exactly, in the faint light of distant galaxies, tells us that space itself is stretching beneath our feet? We begin with something almost childishly simple. The color of light from faraway galaxies is not quite what we expect it to be. Imagine standing on a city street late at night. Somewhere behind you, an ambulance appears, siren wailing. As it rushes toward you, the pitch of the siren sounds higher, almost strained. As it speeds past and races away, the pitch drops, becoming lower and softer. Nothing about the siren itself has changed. What changed is the spacing of the sound waves reaching your ears. As the ambulance approaches, the sound waves bunch together. As it moves away, they stretch out. This effect has a name in physics, the Doppler effect. It is not a fancy idea at its core. It simply says that waves from a moving source will be squeezed or stretched, depending on whether the source is coming toward you or going away from you. Light is also a kind of wave. It usually does not feel that way in daily life, because we mostly experience it as brightness and color, not as a rippling pattern. But in the language of physics, each color corresponds to a certain spacing of these ripples, a certain wavelength. Blue light has shorter wavelengths, packed more tightly. Red light has longer wavelengths, more spread out. Now imagine replacing the ambulance with a distant galaxy. Instead of a siren, it sends out light in all directions. If that galaxy is moving away from us, the ripples of its light get stretched on their journey. In the same way that the sound waves from the receding ambulance spread out, the result is that the light becomes slightly redder than it was when it was emitted. We call this change redshift. The word sounds technical, but it literally just describes what happens. The pattern of light from a distant object shifts toward the red end of the rainbow, compared to where we would expect it to be if the object were at rest. Astronomers learned to measure this shift by carefully splitting light into its component colors, like passing sunlight through a prism. Instead of a smooth rainbow, they focus on thin, dark, or bright lines in the spectrum. Those lines come from specific atoms in the stars, each atom leaving behind a kind of fingerprint at a particular color. When those fingerprints appear slightly displaced toward red, it tells us the light has been stretched. When people first started to notice these shifts in the light from galaxies, they could have meant many things. A galaxy might be moving through space, carried by some initial push. The universe might be full of random motions, like bees in a swarm. Or perhaps there was a pattern hiding in those colors, something deeper than individual galaxies flying around. What emerged from the data, slowly and with a lot of resistance, was not a random swarm. When astronomers plotted how much the light from each galaxy was redshifted against how far away that galaxy seemed to be, they found a relationship. The more distant a galaxy is, the more its light is shifted toward red. The farther it is, the faster it appears to be receding from us. That statement sounds innocent, but it is one of the most important observational facts about the universe we live in. It is a clue that space itself is stretching. Think again about the balloon with dots on its surface. If you inflate it, every dot moves away from every other dot. If you happen to live on one of those dots and you measure the others, you will find that the more distant dots seem to be receding faster. That is not because your dot is special. It is because the surface itself is expanding. In the same way, if the fabric of space is expanding uniformly, then any observer, anywhere, will see the same pattern. Galaxies further away show larger redshifts. The relationship between distance and redshift becomes a signature of expansion, not of a special explosion from one favored point. This is what the data shows us. Not an isolated group of galaxies flying apart into emptiness, but a systematic stretching of the distances between them. There is a subtle but important twist here. For nearby galaxies, redshift can be thought of in the same way as the sound from an ambulance, as a Doppler effect due to motion through space. But on very large scales, over vast cosmic distances, the dominant effect is not galaxies moving like bullets in some pre-existing container. It is the container itself changing, the stretching of space between the galaxies. The light is not just shifted because the source is moving through a fixed background. It is shifted because the background has grown while the light was in transit. To make sense of all this, cosmologists lean on a principle that is almost philosophical. It is called the cosmological principle. And it says, roughly, that on very large scales, the universe is homogeneous and isotropic. Those are heavy words, but the idea is gentle. Homogeneous means that, averaged over big enough regions, the universe looks roughly the same from place to place. Isotropic means that it looks roughly the same in all directions. There are local exceptions. Of course, nearby, there are clusters of galaxies, voids, filaments, but step back far enough, and the patterns even out. If that principle holds, then we are not at a privileged location. We are not at the center of an explosion. We are simply sitting on one galaxy among many, watching space behave in a way that would look similar from almost any other galaxy. The pattern of redshifts is not a sign that the universe is expanding away from us. It is a sign that the universe is expanding everywhere. This interpretation is not just a neat story imposed after the fact. It is tightly bound to the equations of general relativity, which relate the distribution of matter and energy to the curvature of space-time. Under the assumptions of homogeneity and isotropy, those equations predict that the universe cannot remain static. Its scale factor, the quantity that describes how big it is on large scales, must change with time. Light traveling through such a universe will have its wavelength stretched as the scale factor grows. We see exactly that stretching in the light from distant galaxies. There are more layers of support. If the universe was smaller and denser in the past, then matter would have been packed more tightly. Gravity would have pulled more strongly. That should affect the way structures like galaxies and clusters form over time. When cosmologists simulate a universe that expands according to the patterns we infer from redshift, they find that the large-scale web of galaxies they get resembles what we actually observe: long filaments, voids, clusters, a cosmic foam that emerges naturally from initial fluctuations in a growing universe. All of this, so far, still feels perhaps like explanation. But underneath the technical language, something more existential is quietly happening. The light from a distant galaxy takes an enormous amount of time to reach us. During that journey, the universe changes. Space expands. The path that light follows is not fixed. It is as if you were walking along a corridor while the corridor stretches. Each step covers a slightly smaller fraction of the remaining distance than the step before. The light is not just moving through space, it is moving with a space that is evolving as it goes. By the time that light arrives, bringing us an image of the galaxy as it was long ago, the distance between us and that galaxy has grown far beyond what it was when the light began its trip. The redshift we measure now encodes both the motion of that galaxy and the history of expansion its light has lived through. To read that light correctly is to admit that the universe is not a stage but a process. Not a fixed container, but a changing relationship between all things. There is also a kind of loneliness in this picture. In an expanding universe, there are galaxies so distant that their light, emitted now, will never reach us. The expansion of space can outrun the effort of light itself to cross it. Over unimaginably long stretches of time, more and more galaxies slip beyond our horizon. They do not vanish. They simply become causally disconnected from us. No signal sent from us can reach them, and no signal sent from them can reach us. We live, then, in a universe where the map of what is and the map of what can ever be seen or influenced are not the same. Expansion ensures that there will always be parts of reality that are permanently out of reach. When we say we know the universe is expanding, we are not just making a claim about distances and velocities. We are acknowledging that we inhabit a cosmos in motion, one in which the very scale of reality changes with time, carrying us into a future where less and less of the universe is accessible. Even in principle, this knowledge does not come from a single measurement or a single clever argument. It comes from a convergence of clues, redshift patterns, the distribution of galaxies, the way structures grow, the way background radiation behaves. Each of these, interpreted on its own, might have alternative explanations, but together they point stubbornly in the same direction. Like Lemaître's equations, these observations do something subtle to our sense of origin. They tell us that the universe was, in the past, denser and hotter, that the distances we see now were once smaller, that if we keep rewinding, the trend does not level off into an eternal steady state. It sharpens. It suggests a time when the density becomes so high and the temperatures so extreme that our current physics begins to fail. The expansion we infer from redshift does not just describe where galaxies are going. It is the thread that lets us trace where they came from. back toward a state that is not simply a smaller version of now, but something qualitatively different. A universe without galaxies, without atoms, perhaps without a meaningful distinction between space and time in the way we understand them. And yet, even with all this, we have not reached the beginning. We have only shown that the story is not static, that there is a genuine arrow pointing from denser to thinner, from hotter to cooler, from smoother to more structured. The expansion makes a past, unlike the present, unavoidable. What it does not do is give us a clear picture of the moment when that past began. For that, we need a different kind of evidence, not from the light of galaxies, but from something more pervasive and ancient, a faint afterglow that fills all of space, whispering of a time when the universe was so hot and so dense that matter and radiation could not yet go their separate ways. The afterglow is not in the light of galaxies, but in a kind of light that comes from everywhere and nowhere in particular, as if the universe itself remembered being young and could not quite stop humming about it. Long before anyone thought about mapping that hum, radio engineers were simply trying to build better antennas. In the middle of the 20th century, two of them, Arno Penzias and Robert Wilson, were working with a large, horn-shaped antenna in New Jersey. It was designed to pick up faint radio signals, the kind you might use to communicate with satellites. They did everything they could to clean the signal. They cooled the equipment. They checked the electronics. They even removed what they politely called white dielectric material left by pigeons nesting in the antenna. Yet no matter what they did, there remained a persistent background noise. It was faint but stubborn. It did not vary with the time of day. It did not care if they pointed the antenna this way or that. It seemed to come from every direction in the sky. In most engineering stories, noise is the enemy. You eliminate it so you can hear what you actually care about. But sometimes, the noise is the message. Around the same time, a group of physicists not far away were working through the consequences of a hot beginning to the universe. If the cosmos had once been in an extremely dense, fiery state, and then expanded and cooled, they reasoned that early radiation should not simply have vanished. It should still exist, stretched by expansion into longer wavelengths, cooled to a much lower temperature, but still present as a faint background, filling all of space. What Penzias and Wilson had stumbled upon, and what the physicists quickly recognized, was that background. Today we call it the cosmic microwave background. Each word in that phrase carries weight. Cosmic, because it does not come from any single star or galaxy, but from the universe as a whole. Microwave, because its wavelengths are longer than visible light, more like the waves used in microwave ovens and radar, sitting between radio and infrared on the spectrum. Background, because it is not a sharp beam or a discrete flash. It is a uniform glow, present in every direction, like a faint, invisible fog of light. When we measure this radiation carefully, we find something remarkable. Its spectrum, the way its brightness varies with wavelength, matches almost perfectly what is called a blackbody curve. A blackbody, despite the name, is not a literal object, but a theoretical ideal, something that absorbs and then re-emits radiation in the most uniform way possible. The cosmic microwave background behaves almost exactly like the glow from such an idealized object at a temperature only a few degrees above absolute zero. Absolute zero is the temperature at which, in classical thinking, all motion of atoms would cease. It is an unreachable limit, but it gives us a reference point. The background radiation corresponds to a universe that has cooled from unimaginable heat down to just a few degrees above that limit. It is as if the universe were an oven that has been turned off for a very long time, but still holds the last traces of warmth from when it was blazing. What makes this glow powerful as evidence is not just its existence, but its uniformity. When satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and later the Planck spacecraft mapped the sky at these wavelengths, They found that the temperature of this background is almost exactly the same in every direction. The variations are incredibly tiny, at the level of roughly 1 part in 100,000. Those small differences, called anisotropies, are deviations from perfect sameness. Anisotropy is just a way of saying not identical in every direction. They are important because they trace the seeds of structure in the universe, slight overdensities and underdensities in the early cosmos that would later grow, under gravity, into galaxies and clusters and the vast cosmic web. But the main story of the microwave background is its near-uniform glow. If you look at the sky at these wavelengths, you do not see a universe dominated by bright points. You see a young universe that was, on large scales, astonishingly smooth. To understand what moment in cosmic history this radiation is showing us, we need to think about what the universe was made of when it was much younger. In the very early stages, the cosmos was filled with a hot, dense plasma. Plasma is a state of matter in which atoms are torn apart into their components. Instead of neutral atoms, you have a sea of bare nuclei and free electrons, all jostling and colliding. In that environment, light cannot travel very far without being scattered, absorbed, or re-emitted. It is like trying to see across a dense fog or inside an opaque cloud. As the universe expanded, it cooled. Eventually, it became cool enough for electrons to combine with nuclei to form neutral atoms, mostly hydrogen and helium. This event is called recombination, though strictly speaking, it was the first combination, not a recombination. The word stuck for historical reasons. When atoms formed, the fog thinned, with fewer free electrons to scatter it. Light could at last travel long distances without being constantly deflected. The universe became transparent. Photons, the particles of light, set off on journeys that would, in many cases, continue for billions of years without interruption. The cosmic microwave background is made of those ancient photons. They last interacted strongly with matter in that transitional era, when the universe was only a few 100,000 years old, and have been streaming through space ever since. In that sense, the microwave background is not a picture of the absolute beginning, but of a later moment when the universe cooled enough to release light into a clear medium. Cosmologists sometimes call the layer from which these photons last scattered the surface of last scattering. It sounds technical, but the idea is simple. Imagine looking at the surface of a star. You are not seeing into its core. You are seeing the layer from which light can finally escape freely. Deeper in, the matter is too dense and opaque. The surface of last scattering for the universe plays a similar role. When we look at the microwave background, we are seeing as far back as light can show us, to the moment when the cosmic plasma turned into a more transparent gas. Beyond that, in time, lies an era that is hidden from view by light itself. This is not just a poetic limitation, it is a physical one. Light from earlier times simply could not travel to us without being scrambled beyond recognition. Asking what the universe looked like before the surface of last scattering is like asking what the inside of a cloud looks like if all you have are the photons that make it to the edge. You can infer some things, but you do not get a clean image. From the pattern of tiny temperature variations in the microwave background, cosmologists extract a great deal of information. The relative heights of the peaks and troughs in its detailed spectrum tell us about the density of matter and radiation, the amount of dark matter, the presence of dark energy, and the overall curvature of space. The fit between the data and the predictions of a hot, expanding universe is striking. Yet even here, we have to be careful about what we are really seeing. The microwave background does not show us galaxies. It does not show us stars. It does not show us the Big Bang itself. It shows us a young universe that is already on its way, already expanding, already cooling, already structured in subtle ways that will later blossom into the complexity we inhabit. It is more like an early childhood photograph than a birth certificate. You can tell, looking at it, that this universe had a hot, dense past. You can see, in the small variations, the hints of future structure. You can measure its average temperature and compare it to what you would expect if radiation from a very hot beginning had been stretched and cooled by expansion. The match is excellent. But if you stare at that image, no matter how detailed your map becomes, you will not see the moment when space and time first became meaningful. The surface of last scattering is a boundary in light. It is the deepest optical memory the universe has left us. This is where the afterglow becomes philosophically unsettling. The more precisely we measure it, the more convincingly it tells us that the universe did have a hot, dense phase. The data from satellites, from balloons, from ground-based observatories all converge. The cosmos behaves exactly as if it began in such a state, and has been expanding ever since. The temperature of the background, its spectrum, the pattern of its fluctuations, all of it lines up with the Big Bang model. At the same time, that very success sharpens the edge of our ignorance. The microwave background does not blur the beginning into a gentle mystery. It brings us right up to a wall and then stops. On our side of the wall, we have exquisite detail. On the far side, we have only theory and speculation. You could say that the universe itself is doing something like what Lemaître did with his equations. It leads us back toward a beginning, then quietly refuses to show us the last steps. Not because it is hiding something in a deliberate sense, but because the laws that allowed light to carry information simply did not yet give us a transparent medium to see through. So the afterglow of the hot beginning is both proof and limit. Proof that there was a time when the universe was far hotter, denser, and simpler than it is now. Limit, because it fixes a horizon in the past beyond which our usual ways of looking simply do not apply. If we want to ask what the universe was like right after it began, we cannot stay with images. We cannot push the microwave background further back as if turning a focus ring. We have to translate that question into something else, into a description of states and scales, of temperatures and densities and forms of matter, and finally into an acknowledgement that, near the beginning, the very language of before and after starts to lose its footing. So when we ask what happened right after it began, we are really asking what lies in the darkness, just behind that glowing wall of memory. The phrase sounds innocent. Right after it began. We say it without noticing the weight packed inside. It assumes there was a beginning in time, like the opening frame of a film. It assumes that time flowed before and after in the same way. Like a river that just happens to start at a particular spring, it assumes that the universe, in those first moments, could be treated as a scene, something that could have been watched from just the right angle. In everyday life, right after is easy. Right after sunrise, the sky is still soft and pale. Right after a glass falls, we hear the shatter. There is a clear sequence, one event, then another, before, then after. Our language leans on that sequence so heavily that we do not notice it. But near the beginning of the universe, those habits break. First, there is the problem of sight. When the cosmos was very young, it was not transparent. It was filled with that hot plasma, a fog of charged particles where light could not travel far without being scattered. Asking what it looked like is already a mismatch. There was no stable view, no clear line of sight. Light was trapped in a noisy crowd of matter. Imagine trying to describe the shape of a room while standing inside a thick cloud. With light bouncing chaotically in every direction, the room still exists. The walls and corners are still there, but the usual idea of seeing them fails. If someone asks what the room looks like, the honest answer is that the question needs to be translated. You can talk about the density of the fog, the way sound carries, the temperature of the air. You cannot give a clean visual image. Something like that happens when we push back to the earliest universe. So cosmology quietly changes the question. Instead of asking, "What did the universe look like right after it began?" it asks, "What was the universe like?" And like here does not mean an image. It means a physical state. How hot was it? How dense? In what form was energy stored? Were there particles as we know them, or only more primitive ingredients? Was space smooth or violently curved? Could light move freely, or was it trapped? Those questions sound colder, less cinematic, but they are the ones that can be answered with some honesty. For a while, after the beginning, the universe was a kind of fluid made of radiation and particles, all coupled tightly together. Radiation, here, just means energy traveling as light and related forms. The particles were the basic building blocks of matter, still far from forming atoms. In that state, the difference between matter and light was blurred by constant interaction. As expansion continued, this fluid cooled. Cooling here does not mean a breeze passing through. It means that as space stretches, the wavelengths of light stretch too, carrying less energy per photon, and the average motions of particles slow. The universe moves from a state dominated by intense radiation to one where matter, in its various forms, begins to shape what happens next. We sometimes say in the first few minutes or in the first hundreds of thousands of years, but those phrases are already compromises. They try to translate an alien regime into human time. They are like using the length of a walk to describe the size of a continent. It gives a handle, but not really an understanding. The deeper issue is not only that the early universe is opaque or that its physics is extreme, it is that, as we move closer to what we call the beginning, the very concepts of before and after become tied to a framework that may not survive the trip. Our clocks, in all their forms, are built from regular processes inside the universe. The swing of a pendulum, the vibration of a crystal, the oscillation of atoms. Even the idea of a second is defined by how many times a particular atomic transition repeats. These are patterns that exist in a cooled, structured, relatively calm universe. Near the beginning, those familiar structures do not exist. The laws we use to extrapolate backwards come from a world of atoms and stars, of stable particles and smooth space-time. When we push them into realms where those assumptions fail, we are extending them beyond where they have been tested. At some point in that backward extrapolation, our confidence should thin. Yes, we can describe the universe when it was young, but still governed by well-understood physics. We can talk about a time when nuclei formed, when atoms formed, when the cosmic fog cleared. We can say, with some rigor, that everything we see today grew out of those earlier states. But when we ask about right after it began, we are trying to peek into a domain where those very laws, written for a smooth space-time, may no longer apply in their present form. Time, as measured by clocks built from matter and light behaving in familiar ways, may not yet have the meaning we are projecting onto it. We can feel this discomfort if we take the phrase seriously. Suppose the universe has been expanding for some finite duration. We can label that duration with a number of years, derived from observations and models. Then we ask, what about a tiny fraction of that duration after the start? What about an even smaller fraction? We can keep slicing that interval into parts as small as we dare. Each slice, mathematically, has a right after, mevasode bis, but if we keep going, we eventually reach a scale where the slices become so small that our usual distinction between this moment and the next stops lining up with any physical process we understand. Quantum effects blur events. Gravity becomes strong at tiny distances. Space-time itself may no longer look like a smooth continuum. This is not just a technical nuisance. It is a warning that the human habit of imagining time as an unbroken line, with a clear starting point and a simple right after, is being applied outside its home territory. So what can we say? Without pretending to know more than we do, we can say that there was a hot, dense phase. That expansion carried the universe from that phase into the cooler, more structured state we see around us now. That radiation and matter were once in thermal equilibrium, meaning they shared a common temperature and exchanged energy freely. That as expansion proceeded, that equilibrium broke and new structures emerged. We can say that, before atoms formed, the universe was a glowing plasma. Before that, particles themselves may have existed in forms only partially accessible to current experiments. Before that, perhaps, the distinction between matter and the underlying fields from which it arises becomes subtle. At some deeper level still, the smooth fabric of space-time that general relativity describes might dissolve into something more granular or more abstract. Various theoretical ideas attempt to capture this, suggesting that space and time emerge from more fundamental ingredients. But here we enter the realm of speculation, where there is beauty in the mathematics but little direct guidance from observation. In this light, the Big Bang is better understood not as a single event that happened at a precise clock time, but as a boundary in our descriptions, a frontier beyond which our current frameworks cannot be trusted. It is a horizon in theory, just as the surface of last scattering is a horizon in observation. When people ask, "What caused the Big Bang?" the question carries a hidden assumption, that the beginning of the universe is like an event inside time, with something before it that could stand in the role of a cause. But if time itself is part of what is coming into being, the relationship between cause and effect cannot be carried backward, unchanged. Cause and effect, as we know them, are patterns within an already existing temporal order. This does not mean that the universe came from nothing in a simple, declarative sense. It means that our usual picture of causes lining up along a timeline may not apply all the way down. Asking what triggered the beginning might be like asking what lies to the north of a point that already marks the northernmost reach of a sphere. The question uses words correctly, but the geometry underneath refuses to answer in the way we expect. So, right after it began ends up being an ambiguous phrase. From the point of view of our current physics, it might refer to the earliest era in which our equations still give meaningful answers. From a philosophical point of view, it might refer to the first moment when time, in any recognizable sense, can be said to flow. From a human point of view, it might just mean as far back as we can reasonably talk without lying to ourselves. I'm my dime. Each of those meanings is different. None of them match the naive image of a fireball exploding into emptiness. There is an odd kind of humility that comes from facing this. The universe we study is old, vast, and structured in ways that we can describe with impressive precision. Yet when we trace it back to its earliest phases, we run into a conceptual fog that is not just about missing data, but about the limits of the ideas we use to define data in the first place. Instead of treating that fog as a temporary embarrassment, cosmology, at its most honest, treats it as part of the landscape. The Big Bang is both a discovery that the universe had a hot, dense past and has been expanding, and a boundary, beyond which our current language bends. To move any closer to that boundary, to talk more carefully about those earliest fractions of cosmic history, we need tools that are less tied to human-centered notions of size and duration. Our meters and seconds, our kilometers and hours, were born from life on a small planet orbiting an ordinary star, near the beginning. Those units are like toys carried into a storm. What we need, instead, is a way of measuring that is anchored not in human convenience, but in the deepest constants of nature themselves, a scale built out of the fundamental properties of reality, not out of our particular place within it. A way of saying, this is small or this is brief, that does not depend on how we happen to live, but on how the universe is. It is a strange kind of honesty, to admit that our own rulers and clocks are parochial, and then try to build new ones that belong to the universe itself. Our usual units are souvenirs of our situation. The meter was once tied to a piece of metal, then to the size of the Earth, and now to how far light travels in a fraction of a second. The second itself is tied to the regular ticking of atoms in a laboratory on a particular planet. Kilograms, joules, degrees, whatever their refinements, they all carry traces of their origin in human bodies, human tools, human environments. For almost everything we do, this is fine. To measure a room, a road, a planet, even a galaxy, these units are more than adequate. They give us numbers we can write down, compare, remember. They let engineers build bridges and spacecraft and telescopes near the beginning of the universe. They become almost comical. If you try to measure the earliest eras of cosmic history in seconds and meters, you end up with exponents piled on exponents. Times so short that they are written as one divided by a number with more zeros than you can comfortably think about. Lengths so tiny that, compared to them, a proton is enormous. Energies so high that they make the output of stars look modest. At some point, you are no longer really understanding anything. You are just stacking symbols. The German physicist Max Planck saw this problem in a different context more than a century ago. He was trying to understand how hot objects glow, why their color changes with temperature in the way it does. To get the right answer, he had to introduce a new constant into physics, a fixed quantity that would later bear his name. That constant, which shows up in quantum theory, sets the scale on which energy comes in discrete packets rather than as a smooth flow. Planck realized that this constant was not just another parameter to plug into equations. Combined with a few other deep constants of nature, it could be used to build a system of units that did not depend on any human choice at all. Those other constants are familiar to physicists. One is the speed of light in vacuum, the maximum speed at which cause and effect can propagate, which also links space and time in relativity. Another is the gravitational constant from Newton's law of gravitation, which measures the strength of gravity. One more is the Boltzmann constant, which connects temperature with energy in statistical mechanics. The branch of physics that describes the collective behavior of many particles. Take these constants together, and you can form combinations that have the dimensions of length, time, mass, energy, and so on. The resulting units are what we now call Planck units. A Planck length is the length you get when you mix the gravitational constant, the speed of light, and the quantum constant in a particular way. A Planck time is the time it takes light to travel one Planck length in vacuum. A Planck mass, energy, and temperature can be defined similarly. The important thing is not the exact formulas, which are hidden behind the algebra, but the idea. These units are built only from the deepest known constants of nature. They are, in that sense, not ours. They are the universe's own units. When you compute their values, you find something sobering. The Planck length is inconceivably small, far beyond the reach of any microscope we can build. The Planck time is an unimaginably brief interval, so short that if you tried to compare it to a second, the ratio would itself be a number beyond ordinary comprehension. The Planck energy is correspondingly enormous. Concentrating that much energy into a region at the Planck length would warp spacetime violently. What does this have to do with the beginning of the universe? The crucial point is that the Planck scale marks the regime where our two great theories of the 20th century collide. On large scales and for strong gravity, general relativity works extremely well. It treats gravity as the curvature of space-time, a smooth fabric. On small scales and for the other forces, quantum theory works extremely well. It treats fields and particles in terms of probabilities, waves, and discrete quanta. At ordinary energies and sizes, we can get away with using these frameworks separately. We use general relativity to describe the motion of planets, the bending of light by galaxies, the expansion of the universe as a whole. We use quantum theory to describe atoms, nuclei, particles in accelerators, the behavior of electrons in solids. At the Planck scale, that separation breaks down. If you try to describe a region of space as small as the Planck length using quantum theory, you find that the uncertainty in energy becomes so large that its gravitational effect can no longer be ignored. Conversely, if you try to describe gravity at those scales using general relativity, you are forcing a smooth geometry onto something that quantum theory tells you is violently fluctuating. The Planck time, then, is not just another tiny tick on a cosmic clock. It is roughly the time scale below which our current physics, as a combined package, cannot be trusted. The Planck length is not just another small distance. It is roughly the scale below which the very idea of a continuous space may cease to make sense. This is why cosmologists say that the Planck Era, the period when the universe was younger than a few Planck times and smaller than a few Planck lengths in a relevant sense, lies beyond our reliable description. It is not that nothing existed then. It is that the tools we use to describe existence were not built for those conditions. The appeal of Planck units, in this context, is that they give us a natural marker. Instead of saying a fantastically tiny fraction of a second after the Big Bang, we can say after the Planck time. Instead of saying at a density so high that every familiar object would be crushed beyond recognition, we can say around the Planck scale, with a prom. These phrases are still metaphors of a sort, but they remind us that the scales involved are not arbitrary. They are set by the intersection of quantum uncertainty, gravity, and the finite speed at which influences can spread. If we use Planck units to describe the early universe, something interesting happens. Many of the extreme quantities that look absurd in human units become numbers of order 1. The temperature near the Planck time is of order 1 in Planck temperature units. The density is of order 1 in Planck density units. Time intervals and lengths become, in a sense, natural. This does not suddenly make the physics simple. It does something more subtle. It emphasizes that the craziness is not in the universe, but in the mismatch between our measuring sticks and the regime we are trying to probe. In Planck units, the frontier of the beginning is not a pile of impossible exponents. It is a place where the dimensionless numbers that describe physical processes are not particularly huge or tiny. That suggests that whatever theory truly describes that regime, some future quantum theory of gravity, perhaps will find its most natural expression there. From the perspective of existential curiosity, Planck units play a double role. On one hand, they are our best attempt to speak in the universe's own language, to define small and brief, not by reference to our lives, but by reference to the deepest patterns we have found in nature. On the other hand, they are also a confession that there is a limit. When cosmologists say that we can talk meaningfully about the universe back to a fraction of a second after the Big Bang, what they really mean is that our current physics can be trusted back to a time somewhat larger than the Planck time. Before that, in the Planck era, our equations are being pushed beyond the domain in which they have been tested. The Planck scale becomes, in this sense, a line drawn on the map with a shaky hand. Here, it says, beyond this point, the details of space and time are no longer well described by the theories you know. Tread carefully. In 3 First Dua, for storytelling, there is a temptation to treat that line as a doorway to answers. To imagine that if we could only invent the right theory of quantum gravity, we would stand on the Planck threshold and look back at the moment of creation with perfect clarity. That the right mathematics, in the right units, would finally let us say exactly what happened at the beginning. It is possible that a future theory will indeed describe the Planck era more completely. It might tell us whether space and time emerge from something more fundamental, or whether the Big Bang is a transition from a previous phase, or whether the concept of before truly dissolves. But even then, Planck units remind us that any such description will not be written for our comfort. The scales it uses are not human ones. The processes it reveals may have no direct analogy in our macroscopic world. The narrative we construct from it will always be, in some sense, a translation. To measure the beginning in Planck units is to accept that we are measuring the limits of our own frameworks at the same time. Each Planck length we talk about is a unit of distance and a symbol of ignorance. Each Planck time is an interval and a reminder that beyond some point, time itself may be the wrong concept. So when we say that the Big Bang happened at a certain finite time in the past, we are really saying that, measured in Planck units. The age of the universe is a large number, large enough that the initial conditions are far behind us, large enough that the details of the Planck era have been washed out by expansion. What we cannot say, with any current confidence, is what the first few Planck times were actually like. Were there already something like space and time, just in a foamy, fluctuating form? Were these concepts themselves emergent, like temperature emerging from the motion of many molecules? Was there a meaningful sense in which one could talk about earlier and later at all? Those questions lead us straight into the next problem. It is not just our units that struggle near the beginning. It is the very structure of gravity itself, and the equations that describe how space-time bends and evolves. When we follow those equations back to the Planck scale, they do not gently fade, they break. When an equation fails, it does not explode. It just starts returning answers that make less and less sense, while still wearing the calm face of certainty. Gravity entered modern physics as a quiet revolution. Einstein's general relativity replaced the idea of a force reaching across empty space with a geometry that responds to matter and energy. Space and time, fused into space-time, are no longer a passive stage. They bend and twist in response to what they contain. Objects then move along the straightest possible paths within that bent stage. Those straightest paths have a name: geodesics. On a flat sheet of paper, a geodesic is just a straight line. On the surface of a sphere, a geodesic is a great circle, like the path of an airplane following the curve of the Earth. In space-time, a geodesic is the path a freely falling object follows when nothing pushes or pulls on it except gravity. General relativity tells us how these geodesics behave when space-time is curved, and how that curvature is created by matter and energy. In that sense, it is an extraordinary success story. It predicts the precession of Mercury's orbit, the bending of starlight by the sun, the existence of black holes, the slow dance of binary pulsars, the stretching of space in cosmic expansion. Tests have confirmed its predictions again and again. But if you give those same equations a different kind of challenge, something else happens. Ask them what occurs if you keep concentrating matter more and more. Or ask what they say if you run cosmic expansion backward far enough. They will give you an answer. And that answer, if read literally, says space-time can be driven to a state of infinite curvature and infinite density. That is what physicists call a singularity. It is easy to picture that as a point, a location where everything is crushed into nothing. But a singularity is not really a place in the ordinary sense. It is a signal. It is the mathematics telling you that, under the assumptions you have made, some quantity you are calculating has blown up beyond bounds. Think of drawing a map of the globe using a particular projection near the poles. Some projections stretch continents into wild shapes. The lines of longitude bunch up in a way that breaks the map's ability to represent distance faithfully. If you did not know about map projections, you might think something catastrophic happened to the Earth at the poles. In reality, what failed is not the planet. But that method of mapping, singularities in general relativity are like that. They are not necessarily telling us that the universe literally contains points of infinite density. They are telling us that, pushed to an extreme, the way we are trying to map space-time has reached its limits. This becomes clearest in the study of black holes. When a massive star exhausts its fuel, gravity can overwhelm all the pressures that try to hold the star up. If enough mass is concentrated in a small enough region, general relativity says that nothing can prevent complete collapse. Space-time around that region curves so strongly that there forms a boundary, an event horizon, from within which no light can escape to the outside world. From our point of view, the event horizon is already dramatic enough. It is a one-way surface, a point of no return. Anything that crosses it, whether a star, a planet, or a beam of light, cannot come back out. But inside that horizon, the equations predict something even stranger. They say that all possible paths into the future lead inexorably to a singularity. The phrase, "into the future," is important. Inside, a black hole, moving toward the singularity is not just falling down a hole. It is as unavoidable as moving from today into tomorrow. Time and space swap roles in a sense. No matter what you do, the singularity lies ahead of you. The way tomorrow lies ahead of today. Yet every serious physicist also believes that the singularity prediction is a sign of incomplete understanding. At densities that high, quantum effects in gravity should become important. The smooth fabric of space-time that general relativity assumes may no longer be a good picture. The singularity is a place where we are trying to apply a theory outside the regime where it can be trusted. This is not an isolated oddity. In the 1960s, Roger Penrose and Stephen Hawking developed a set of theorems that made the problem harder to ignore. Using general relativity itself, and only very basic assumptions about matter, they showed that singularities are not rare, pathological cases. Under quite general conditions, if a gravitational collapse leads to an event horizon, or if the universe is expanding in a certain way, geodesics cannot be extended indefinitely into the past or future. This idea has a technical name, geodesic incompleteness. It means there are paths through space-time that simply stop after a finite amount of proper time, even though nothing obvious prevents them from continuing. That is a way of stating, in the language of the theory, that there is an edge. In the context of a black hole, that edge is the singularity you would encounter after falling in. In the context of the entire universe, it becomes something like a Big Bang singularity in the past. Geodesics, if extended backward, hit a boundary where the curvature becomes unbounded and the equations no longer give sensible answers. So general relativity, when taken seriously, does not gently hint that there might have been a beginning. It insists that, under its own rules, there is a limit in the past beyond which it cannot represent space-time as a smooth manifold at all. The theory bends back on itself and points to its own breakdown. This is a remarkable situation. The most successful description we have of gravity, one that has passed every experimental test we have been able to devise in regimes we can access, contains within it a proof that it cannot be the final story. It predicts its own failure in the most extreme conditions. In everyday science, when a theory fails, we usually discover it by comparing its predictions with an experiment and finding a mismatch. Here, the warning comes from inside. The equations flag a regime where they return infinities. No one can perform an experiment in the singularity at the center of a black hole, or at the putative origin point of cosmic time. The theory itself tells us, do not trust me there. For our question about the beginning, this is both clarifying and unsettling. On the clarifying side, it means that we should stop imagining the Big Bang singularity as a literal physical point. where all the mass and energy of the universe were stuffed into a zero-sized dot. That picture is not what the mathematics truly supports. The singularity is the horizon of the theory, not a little marble at the origin of space. On the unsettling side, it means that when we talk about the universe emerging from a Big Bang singularity, we are leaning on language that suggests more understanding than we possess. General relativity can describe an expanding universe very well, as long as we stay a safe distance away from that singular boundary in time. It can tell us how galaxies move, how space stretches, how light is redshifted. It can trace that history back to very early, very dense, very hot states. But as we approach the domain where quantum gravity should matter, the theory does not smoothly connect to a description of what came before. It simply reaches a point where its own internal logic says, "Here, my geodesics end." You can feel the philosophical weight of that if you sit with it. Gravity, in general relativity, is not a force among others. It is the structure of space and time themselves, and that very structure, when asked to describe its own origin, becomes silent. There is also a more subtle difficulty. Some people hear about singularity theorems and think, so the universe must have had a beginning in time. Full stop. Others, uncomfortable with that idea, look for ways around it. They consider exotic forms of matter that violate some of the assumptions of the theorems. They consider alternative theories of gravity. This scientific work is valuable. It explores possibilities. But from the standpoint of existential understanding, the conclusion is not that we can now say definitively whether the universe really began or not. It is that even our best attempts to formalize the notion of a beginning or of an eternal past rely on frameworks that break under pressure. If you try to construct a model in which the universe has always existed, you must confront the same issues of quantum gravity and singular behavior in some guise. If you construct a model in which the universe has a definite starting time, you must confront the absence of a clear cause within time for that start. In both directions, the trail of reasons thins out. This is why the language of "before the Big Bang" is so treacherous. General relativity, taken literally, does not contain a region of space-time that lies before its own singularity. Time, in that model, simply does not extend past a certain point. Asking what happened earlier is like asking for a continent beyond the edge of a globe. Yet, our instincts resist this. We are so used to every event having a prior cause, every story having an earlier chapter, that we feel compelled to imagine some pre-Big Bang domain where something happened to bring the universe into existence. Our equations do not currently support that picture in any straightforward way, nor do they support the comforting alternative of an infinite, unchanging past. So we are left in a peculiar position. The gravitational equations that describe the growth of structure, the bending of light, the orbit of planets, and the expansion of the universe also tell us, rigorously, that there is a boundary to their competence in the past. The closer we get to that boundary, the more they whisper, "Beyond this, you will need something else." This is where the search for a quantum theory of gravity becomes more than a technical project. It is an attempt to find a language in which questions about the earliest universe and about the interior of black holes can be asked without immediately triggering infinities. A language in which space and time are not assumed to be smooth all the way down. From the point of view of meaning, this does something quiet but deep. It suggests that the failure to picture the beginning is not just a failure of imagination, it is a reflection of the way our current laws of nature are structured. They are extraordinarily good at describing a universe that already exists, already has a space-time manifold on which events take place. They are not built to answer why there is such a manifold at all, or what it is like at the boundary where its own description fails. The breaking of the gravitational equations at singularities is, in that sense, not just a technical glitch in the story of the Big Bang. It is the universe telling us that the story we are trying to tell, in terms of continuous space and time stretching all the way back, cannot be extended indefinitely. To go further, we have to descend beneath that smooth picture into the realm where quantum behavior reigns. There, particles do not behave like tiny stones, but like smeared possibilities. Fields fluctuate even in their lowest energy states. And whatever gravity becomes in that domain, it will not look like a gentle bending of a continuous fabric. Beneath that smooth fabric that tears at singularities, there is already a quieter logic running. One that does not believe in crisp edges or perfectly solid paths. We call that logic quantum theory. In ordinary life, it is invisible. Tables stay where you put them. Planets follow predictable orbits. Light seems to travel in straight lines from lamps to walls. You can point at a chair and say, with confidence, that it is here and not there. Quantum theory begins to matter when we look at things that are very small or very light. Atoms, electrons, the smallest chunks of energy we know how to talk about. At that scale, the universe does not behave like a set of tiny billiard balls colliding in a vast, empty room. Instead, it behaves like something that cannot decide, in advance, which of several futures it will commit to. One of the most basic ideas in quantum theory is superposition. The word sounds technical, but it simply means that a system can carry several possibilities at once. An electron, for example, can behave as if it is in more than one place at the same time, or as if it has more than one possible value for some property, until we make a measurement that forces it to reveal a single outcome. This is not just a poetic way of saying we are ignorant. Superposition is built into the equations that successfully predict experiments. When physicists calculate what might happen in a quantum process, they do not assign a single path. They add together many possible paths, each weighted by a kind of amplitude, a number that encodes how likely that path is to contribute. The mathematics that describes this is called a wave function. Again, the phrase can sound abstract, but the idea is that instead of saying, the particle is here, we say, the system is described by a wave of possibilities spread out over many locations and states. The wave function does not sit in space the way water does. It lives in a more abstract space of possibilities, but it lets us calculate probabilities for different measurement outcomes with sharp accuracy. Then there is the uncertainty principle. This is a rule that says there are pairs of quantities we cannot know with unlimited precision at the same time. Position and momentum are the classic pair. The more precisely you know where something is, the less precisely you can know how fast it is moving and in which direction, and vice versa. Uncertainty here is not about bad instruments or human clumsiness. It is a built-in feature of the world at the quantum level. Taken together, superposition and uncertainty are trying to tell us something uncomfortable. At the deepest scales we have probed, reality is not a collection of tiny objects, each carrying definite properties all the time. It is a web of potentialities, structured by rules that give crisp probabilities, but not a single, fully determined story. If this sounds like a philosophical interpretation, it is worth remembering how concrete quantum theory is in practice. Every time you use a device with a semiconductor inside, you are relying on quantum rules that govern how electrons move through a solid. Those rules explain why some materials conduct electricity well and others act as insulators. They explain the existence of transistors, which are the building blocks of modern electronics. Lasers depend on another quantum effect, stimulated emission, where atoms release light in a coordinated way, when perturbed just right. Magnetic resonance imaging, the medical technology that lets doctors see inside the body without cutting it open, is based on the quantum behavior of atomic nuclei in magnetic fields. All of these technologies would simply not work if quantum theory were just a strange story. They work because the equations, as odd as their implications are, describe something real about how nature behaves at small scales. If quantum effects stayed locked in the microscopic world, we might treat them as a curiosity, but they do not. They leak outward in subtle ways. One of the most striking is entanglement. When two quantum systems interact in certain ways and then separate, they can remain linked such that their properties are correlated beyond what any classical picture would allow. Measure one here, and the outcome is related to what you will find if you measure the other there, even if they are far apart. Entanglement does not allow faster-than-light communication. It does not let us send messages instantaneously, but it does tell us that the quantum description of the world is not one in which each part carries its own independent set of properties. The whole can be in a state that cannot be broken down into local pieces without losing something essential. Underneath the familiar reality of objects and distances, then, there is a level at which the universe behaves less like a collection of separate things and more like a single, interconnected system of possibilities. Quantum theory also changes how we think about emptiness. In classical physics, a vacuum is simple, an empty box with nothing in it. In quantum theory, the vacuum is restless. Even in what we call empty space, fields are present. A quantum field is like a fabric that fills all of space, with excitations of that field corresponding to particles. There is an electron field, a photon field, and so on. Even when these fields are in their lowest energy state, they are not perfectly still. Quantum uncertainty allows them to fluctuate slightly. These fluctuations are called vacuum fluctuations. They mean that at very small scales and over very short times, pairs of particle and antiparticle can briefly appear and then annihilate each other again, borrowing energy from the vacuum and returning it quickly enough that no conservation law is violated in a measurable way. This picture sounds almost mystical, but it leads to real, observable effects. For example, the forces between charged particles are influenced by virtual particles flickering in and out of existence in the vacuum. Experiments that measure the magnetic properties of the electron and other quantities confirm these predictions to an astonishing degree of precision. So the quantum world beneath familiar reality is not a ghost story. It is a carefully tested, highly predictive framework that simply tells us that our everyday intuitions about particles, positions, and emptiness are incomplete. Now bring this back to the early universe. In the first instance after the beginning, whatever exactly that means, densities and energies were extremely high. The quantum fields that describe matter and radiation were not in the calm, nearly empty state that we observe today on large scales. They were excited, interacting intensely, fluctuating. Even in slightly later eras, when the universe had cooled enough for classical descriptions to start making sense again, quantum fluctuations would still have been present. In many models of the early universe, tiny quantum ripples in the density of matter and energy are stretched by cosmic expansion into the seeds of the large-scale structure we see today. In that view, the galaxies and clusters and voids that form the cosmic web are not just random arrangements. They are the grown-up shapes of ancient quantum fluctuations, blown up to cosmic size. There is something quietly profound about that. The places where stars would gather, the regions that would become dense enough to form planets, are determined in part by quantum chance early in the universe's history. On that picture, the fact that you exist in this galaxy, around this star, on this planet, is connected to patterns of quantum fluctuations that took place when the cosmos was incomprehensibly young. At the same time, quantum theory by itself does not tell us how space-time behaves when it is under extreme gravitational stress. The standard form of quantum theory assumes a fixed background of space and time on which processes play out. General relativity, by contrast, says that space-time itself is dynamic, shaped by what it contains. If we try to apply ordinary quantum rules to a gravitational field that is itself changing, we encounter deep tensions. Time in quantum theory is usually treated as an external parameter, something we measure against. In general relativity, time is part of the geometry that can bend and warp. This tension becomes unavoidable near the beginning of the universe. The densities are so high, the curvatures so extreme, that we cannot treat gravity as a static backdrop. It should be fully quantum. Yet our current quantum theories are not built to handle that properly. You can feel, again, the limits of language pressing in. The quantum world wants to replace definite trajectories with probability waves. General relativity wants to replace forces with curvature. When we try to let them speak at the same time, their grammars clash. Still, for a significant stretch of the early universe, we can use quantum theory in a more modest way. We can treat fields like the inflaton, a hypothetical field that may have driven a period of rapid expansion, as quantum objects. Their fluctuations can be computed using standard techniques. Then we can feed those fluctuations into a classical description of how gravity responds. This hybrid approach is not fully consistent at the deepest level, but it works remarkably well in matching observations, such as the pattern of temperature variations in the cosmic microwave background. The statistical properties of those variations, their near-scale invariance, and their slight departures from perfect uniformity, fit naturally with the idea of quantum fluctuations stretched by inflation. So quantum theory, even in this incomplete role, already shapes our understanding of what right after it began might mean. Not a tidy sequence of events laid out along a single, sharply defined time axis, but a period in which the universe is described by fluctuating fields and probabilities, with certain patterns amplified by expansion into the scaffolding of everything we will later call structure. From an existential angle, there is a temptation to read this as a story of fundamental indeterminacy. To say, at the base of reality, there is no script, only chance. But quantum theory is stranger than pure randomness. It offers not just arbitrary outcomes, but a precise rule for how likely each outcome is, encoded in the wave function. The world is not determined in advance, but neither is it simply chaotic. It is constrained unpredictability. When we apply this to the early universe, any simple question like, could it have been otherwise, becomes difficult to phrase. In some interpretations, one might say that all allowed histories contribute to the overall description, each weighted by its quantum amplitude. In others, one might say that the universe chooses one history randomly according to those weights. Either way, the neat picture of a single, inevitable cosmic beginning, written like a fixed opening chapter, starts to dissolve. In its place, we get a more unsettling vision, a reality where possibilities and probabilities are as fundamental as objects and events, and where the emergence of the universe we inhabit is tied to those deep statistical rules. Quantum theory, then, does not rescue us from the strangeness of the beginning. It deepens it. It tells us that beneath the apparent continuity of space and time, there is a layer of description where certainty is replaced by amplitude, where emptiness seethes, and where connections can exist between distant parts of the universe that defy classical intuition. To understand the earliest moments in any serious way, we have to bring that quantum world together with gravity, rather than letting them operate in separate domains. We need a framework in which space-time itself can be in superposition, fluctuate, perhaps even be entangled with other degrees of freedom. That search has been going on for decades. It has produced candidate ideas with names that sound like science fiction: loop quantum gravity, string theory, causal sets, emergent space-time. Each offers a different way of thinking about what lies beneath the familiar surface of reality. Each tries, in its own way, to answer the question of what happens when you let quantum rules act on gravity itself. None of them, so far, has given us a final, universally accepted picture, but all of them point toward the same conclusion. If we hope to say anything honest about the universe at the very threshold of its beginning, we must let go of both classical certainty and classical geometry. The foundation will not be a smooth fabric gently curving, nor a set of tiny particles marching along clear paths, but something that merges both into a deeper, more abstract structure. And even if we find that structure, even if we learn to write equations that behave well at Planck scales and through singularities, we will still face a quieter, human question. What does it mean to live in a universe whose origin is written in a language that was never meant to comfort us? We look for that language anyway, knowing in advance that it will not speak in the metaphors we grew up with. The search for quantum gravity begins from a simple tension. We have two astonishingly successful descriptions of reality, and they disagree about what is allowed to move and what is allowed to be uncertain. Quantum theory, as we have seen, treats fields and particles as fundamentally probabilistic. It wants a fixed stage, a background space, and a background time on which events can unfold, like actors moving on an already built set. That background is not usually part of the quantum game. It is just there. General relativity, by contrast, says that the set is not pre-built. The stage flexes. Space and time are not passive coordinates but dynamic participants. They curve, ripple, and respond to what they contain. There is no fixed grid beneath everything. No absolute clock ticking in the corner. These two attitudes are hard to reconcile. When we use quantum theory in ordinary situations, we assume a clear notion of time that marches forward uniformly, the way the hands of a clock turn. We assume a clear distinction between here and there, encoded in a rigid geometry. In general relativity, those very notions are determined by the distribution of energy and matter. If you change what is in the universe, you change the clocks and the rulers. In the early universe, and inside black holes, we cannot pretend that the geometry is fixed. The gravitational field is not a gentle, static background. It is wild, strong, rapidly changing. To describe those conditions honestly, we would need a quantum theory in which space and time themselves are subject to uncertainty, superposition, and perhaps entanglement, just like everything else. That is what quantum gravity aims for. A framework in which gravity is not an exception to the quantum rules, but another expression of them. There are, broadly, two kinds of strategies people have pursued. In one, you take the quantum language we know and try to apply it directly to the gravitational field. You start from general relativity and attempt to quantize it, which means treating the geometry of space-time as a field that can have quantum fluctuations, like the electromagnetic field. When physicists follow this path, they run into a technical problem that points to something deeper. When they calculate how quantum corrections modify gravitational interactions at very small distances, the integrals that represent those corrections blow up. They diverge more severely than in the quantum theories of the other forces. In other areas of physics, such divergences can often be tamed by a procedure called renormalization. That word can sound opaque, but the basic idea is that you absorb certain infinities into redefined values of physical constants. You admit that quantities like charge and mass are not fixed at all scales, but depend on the energy at which you probe them. After this careful bookkeeping, the theory gives finite, testable predictions. Gravity resists this healing. When treated like an ordinary quantum field, its divergences multiply in ways that cannot be cured by the usual techniques without introducing infinitely many parameters. That would rob the theory of predictive power. The rough message is that gravity, when naively quantized, tells us we are using the wrong language. The straightforward attempt to make space-time just another quantum field, fluctuating atop a fixed background, leads to a swamp of infinities. The second broad strategy is more radical. Instead of quantizing general relativity directly, you look for a deeper structure from which both gravity and quantum behavior emerge as different aspects of one underlying theory. String theory is one example. It replaces point-like particles with one-dimensional objects, strings, whose different vibration patterns correspond to different particles. In some versions, these strings live in more than the familiar 3 dimensions of space and one of time. Extra spatial dimensions are curled up tightly, beyond direct observation. In string theory, gravity appears not as something put in by hand, but as one of the vibration modes of the string, a mode that behaves like a particle called the graviton, the hypothetical quantum of the gravitational field. This is appealing. Gravity and the other forces are unified as different notes played by the same fundamental object. But string theory comes with its own conceptual baggage. It often relies on a background spacetime to define the strings in the first place. That means it does not fully solve the problem of making the geometry itself a dynamic quantum object, at least not in its most straightforward formulations. And while it has led to deep mathematical insights, direct experimental tests of its predictions are far beyond our reach. Another approach, loop quantum gravity, starts from the opposite end. It takes seriously the idea that space-time itself should be fundamentally discrete at the smallest scales, like a woven fabric made of individual loops. Instead of treating gravity as a field on a background, it attempts to quantize the geometry directly, leading to a picture in which areas and volumes come in tiny, indivisible units. In that picture, the smoothness of space-time at large scales is an approximation, much as a fluid seems continuous even though it is made of molecules. The hope is that by building gravity in this background-free way, one can naturally avoid singularities. The fabric cannot be squeezed into a point if it is made of finite loops. Loop quantum gravity, too, has its challenges, connecting its discrete structures cleanly to the smooth world we see. Recovering familiar physics at scales we can test is a subtle task. Like string theory, it remains incomplete, a work in progress rather than a finished description. Beyond these two, there are other ideas. Some researchers explore the possibility that space-time is not fundamental at all, but emerges from more primitive entities, such as abstract networks of relations or patterns of entanglement. In these views, geometry is a kind of collective behavior, like temperature, which does not make sense for a single molecule but emerges for many. In such scenarios, asking what was space-time like at the beginning might be like asking what water was doing. Before there were enough molecules to make a liquid, the question needs translation. Perhaps there were more basic ingredients interacting in ways that did not yet have a spatial interpretation. All of these programs are speculative. They are guided partly by mathematical elegance, partly by the desire to cure the infinities that plague naive quantum gravity, and partly by hints from black holes and cosmology. They all share another difficulty. The energies at which quantum gravity effects become dominant are so far beyond our current technology that building an experiment to test them directly seems almost impossible. The Planck scale is not just small and brief. It is practically unreachable. The most powerful particle accelerators on Earth can probe interactions at energies many orders of magnitude below the Planck energy. To reach Planck energies with a conventional accelerator, you would need a machine the size of a galaxy, or something equally absurd. That is not simply a matter of funding or engineering. It is a fundamental limitation of our ability to recreate the conditions of the very early universe in a controlled way. So quantum gravity finds itself in an unusual position. It is a field of study that is motivated by the known breakdowns of our best theories, but it lacks direct experimental feedback in the regimes where it matters most. Physicists have not given up. They look for indirect clues. Subtle imprints of early universe quantum gravity effects might be present in the pattern of cosmic microwave background fluctuations, in the distribution of galaxies, or in the behavior of black holes as they radiate slowly over immense times. The famous prediction that black holes should emit a faint glow due to quantum effects near the horizon is one such hint. Although observing that glow in astrophysical black holes is extraordinarily difficult, there are also thought experiments that probe the consistency of different candidate theories. Can they explain why black holes seem to have entropy, a measure of disorder, proportional to their surface area rather than their volume? Can they make sense of what happens to information that falls into a black hole? Do they allow for space-time to be reconstructed from patterns of entanglement in a more abstract quantum system? These are deep questions, but they are not the kind of questions most people have in mind when they ask about the beginning of the universe. They do not feel like, what happened then? They feel like, what kind of thing is space-time? Really? If you can sides, and yet, that is exactly the reframing that quantum gravity forces on us. Once we accept that our classical description is a coarse-grained view, that beneath continuous space and time there may be a more granular or more abstract structure, the idea of a singular beginning becomes even harder to pin down. If space-time emerges from something else, then the beginning of the universe might correspond to a transition in that underlying system. Not a moment when everything popped out of literal nothingness. But then we have to ask, what is the right notion of time in that deeper level? Does it make sense to speak of a before and after for the emergent space-time, or is time itself an emergent parameter, meaningful only within the universe we inhabit, not outside it? Quantum gravity research, in its most honest form, keeps these questions open. It does not pretend that a single elegant equation will someday erase our unease. If anything, the more we learn about possible quantum structures beneath geometry, the clearer it becomes that our everyday temporal concepts may not survive unchanged. For cosmology, this has a sharp consequence. When we say that our current theories take us back to a certain earliest phase after the Big Bang, we are not just hitting a wall of missing data, we are hitting a wall of missing language. Quantum gravity aims to supply that language, but there is no guarantee that, once we have it, the story it tells will satisfy our desire for a simple origin. It may say that the Big Bang is a bounce, a transition from a previous contracting phase to an expanding one. It may say that there was a pre-geometric phase where space and time as we know them did not exist, only algebraic relations among abstract degrees of freedom. It may say that the universe is one branch of a larger quantum state, with many other branches where different histories unfold. Or it may say something that does not presently fit any of our metaphors. In all of those scenarios, the phrase, "what happened before," loses its usual bite. Either there is no meaningful before in our sense, because time itself emerges only after some transition, or there is a more general notion of evolution that does not map neatly onto our experience of past and future. From a human point of view, this can be disorienting. We are accustomed to stories where understanding means fitting events into a narrative sequence. First this, then that. Because of this, quantum gravity threatens to replace that with something like, here is the structure within it. Certain histories have non-zero weight. Among them is one that looks like your universe expanding from a hot, dense state. We can, perhaps, translate that back into a story, but it will always be a translation. So the search for quantum gravity is not just a technical project about unifying equations. It is a slow, collective effort to find out how far our deepest concepts can bend before they break. How far we can stretch the idea of time, of cause, of space, before they stop serving us. It is also an exercise in restraint. Without direct experiments at Planck energies, Theorists must be careful not to mistake mathematical beauty for truth. A theory can be elegant, self-consistent, and rich in structure, yet still fail to describe our universe. The only anchors we have are the places where quantum gravity ideas touch lower energy physics, cosmology, and black hole thermodynamics, in ways we can check. In that sense, quantum gravity lives on a narrow ledge between what we know and what we cannot yet test, too far towards speculation. And it becomes pure metaphysics, dressed in symbols. Too far toward conservatism, and it ignores the clear signs that our current picture of space-time is incomplete. For our question about the Big Bang, the lesson is modest, but profound. We should not expect a quantum theory of gravity to hand us a simple answer like, "This is the moment the universe began," or recliner, "This is what it looked like right after." We should expect it to reshape the question. Instead of chasing an image of the first instant, we may have to learn to live with a description in which beginnings are not points, but phases. Not instants, but changes in the underlying rules. The universe, in such a picture, does not sit inside time. Starting at a particular tick of a cosmic clock, time is part of its internal bookkeeping, arising from whatever deeper structure quantum gravity reveals. Standing here, on the side of ignorance, all we can say is that any honest account of the earliest universe must pass through this narrow doorway. It must acknowledge the clash between quantum theory and general relativity, admit the breakdown of classical geometry at extreme densities, and accept that our familiar ways of talking about before and after may not apply all the way down. Beyond that doorway lies a regime that different quantum gravity programs try to sketch in different ways. However they resolve it, they all converge on one unsettling idea. There is a domain of the universe where space and time, as we know them, are not fundamental. And if we want to ask what the universe was like right after it began, we will have to follow the question into that domain, knowing that we may not recognize the answer as a beginning in any ordinary sense. If there is a level where space and time are not yet themselves, then the phrase earliest universe stops pointing to a place and starts pointing to a kind of strangeness. Physicists give that strangeness a name, the Planck Era. It sounds almost modest. An era suggests something like the age of dinosaurs or the age of steam. In reality, the Planck Era is not an era in any familiar sense. It is a label for the domain where our theories, as they are currently written, lose the right to be taken literally, to even say when it happens, or how long it lasts. We quietly lean on the Planck units we built earlier. Planck time, Planck length, Planck energy. These are the scales at which quantum effects in gravity are expected to become dominant, where treating space and time as smooth and continuous likely stops working. In that regime, the usual picture of space-time as a calm fabric, perhaps gently curved, is replaced by something more like a storm at the smallest conceivable scales. Some physicists use the phrase quantum foam to gesture at this. Foam is an image drawn from ordinary life, a mass of bubbles in turbulent water, constantly forming and collapsing, with no stable shape. The term is not a literal description of what space-time is. It is an attempt to capture, in everyday language, the idea that at the Planck scale, the geometry of space and time itself may be fluctuating wildly. In this imagined foam, distances are not fixed, but are subject to jitter. The notion of a straight line between two points becomes fuzzy. The idea of a smooth surface dissolves into a froth of transient structures. Some models suggest that tiny, short-lived tunnels in space-time, microscopic wormholes, could appear and disappear so quickly that they never become macroscopic objects, but still make the underlying geometry fundamentally rough. Even if such wormholes are only metaphors for deeper mathematics, the core idea remains. At the Planck scale, we should not expect the fabric of the universe to be a continuous cloth. we should expect it to be granular, or network-like, or something even more abstract, with smoothness emerging only when you zoom out. If that is the case, then asking what the universe looked like during the Planck era is already a category mistake. Looking requires light, following reasonably well-defined paths through a reasonably well-defined geometry. But in a regime where geometry itself is fluctuating, even the concept of a light ray becomes uncertain. It is tempting here to imagine a sequence. First, there is the Planck era, where everything is wildly quantum. Then, at some slightly later time, space-time calms down, averages out into something smooth, and ordinary physics takes over. That is not entirely wrong as a storyline, but it hides the depth of the problem. The Planck era is not simply a very early time in a pre-existing temporal flow. It is the domain where the very notion of time as a smooth parameter may not be meaningful. The equations we currently use to define cosmic time, to say now and a moment earlier, assume a space-time already described by general relativity. They assume a geometry that can be sliced into successive instants, about a strime, near the Planck scale. Those assumptions fail. Whatever replaces them will probably not think of time as a single continuous axis along which events are organized. It may treat time as something that emerges from correlations between more basic quantities. It may assign different effective times to different processes, or it may use a structure that does not resemble a time axis at all, only approximating one in certain limits. So, when we speak of the Planck era as if it were a segment on a cosmic timeline, we are already translating a more alien picture into the language of before and after. There is no guarantee that the universe at that level has any internal perspective that would agree with our sense of duration. Still, we can try to circle the edges of this fog. We know that as we run our classical cosmological equations backward, ignoring quantum gravity, we encounter densities and temperatures that grow without bound. The curvature of space-time becomes extreme. Past a certain point, those classical equations flag their own breakdown. The Planck units sit roughly at that threshold. From the quantum side, we know that fields fluctuate even in their lowest energy states. We know that trying to localize too much energy in too small a region tends to create strong gravitational effects. Combine these hints, and we get a picture in which any attempt to probe distances smaller than the Planck length, or times shorter than the Planck time, would inject so much energy that a tiny black hole forms, or space-time buckles dramatically. In other words, the universe seems to protect itself from being resolved beyond a certain sharpness. Try to look closer, and the act of looking changes the thing you look at in a catastrophic way. That is not a convenient engineering limitation. It is a sign that the very idea of closer may not make sense beyond that point. Inside this Planck regime, familiar categories blur. The distinction between matter and geometry may no longer hold. In general relativity, matter tells space-time how to curve, and space-time tells matter how to move. In a quantum gravity regime, that back and forth may be replaced by a single structure in which what we call matter and what we call geometry are two ways of looking at the same underlying degrees of freedom. Think again about temperature. A single atom does not have a temperature in the way a gas does. Temperature is a property of a large collection of atoms, a measure of their average motion. It emerges when you look at many things together. In some proposals for quantum gravity, space-time itself is like that. A single microscopic unit of whatever the fundamental structure is does not have a length in the way a macroscopic rod does. Distance, duration, curvature emerge only when you look at many microscopic elements together and describe their collective behavior. If that is right, then during the Planck era, we may be dealing with a universe that is not yet well approximated by any smooth geometry. It would be like trying to talk about the flow of water when there are only a handful of molecules. The words flow and current are not yet appropriate. The realm is pre-hydrodynamic. The Planck era would then be pre-geometric. It is here that phrases like quantum foam can be both helpful and misleading. They suggest motion and bubbling, which are still spatial analogies. But the true underlying structure might not live in space at all. It might be some abstract network of relationships that only looks like space-time when you coarse-grain it, when you blur out the details. From this perspective, the Big Bang singularity of classical cosmology takes on a different meaning. It is not a literal place where everything was crushed. It is the point in our coarse-grained description where the approximation of a smooth space-time ceases to be valid. Beyond that, we need the deeper quantum description. Of course, we do not yet have that description in final form. We have sketches from string theory, in which geometry can be traded for other structures, and from loop quantum gravity, in which areas and volumes are quantized. We have toy models, in which space emerges from patterns of entanglement in a more abstract quantum system. Some versions of these models suggest that the Planck era replaces the classical singularity with a bounce. In such scenarios, a previous contracting universe shrinks until quantum gravity effects become dominant, prevent a total collapse, and then drive a re-expansion. What we call the Big Bang would then be more like a rebound than a beginning from nothing. Other models suggest that the Planck regime is a kind of one-way transition. There is no earlier classical phase. But the notion of time before a certain point is simply not defined in the way we understand. The Planck era is not a bridge from an earlier universe to ours, but the phase in which the ingredients of our universe crystallize out of a more fundamental, timeless structure. There are even ideas in which multiple regions of space-time can bud off from some deeper reality, like bubbles in a pot that never runs out of simmering. In those pictures, the Planck regime may be where individual bubble universes are born, each with its own emergent space and time. What all these speculations share is not their specific imagery, but their admission that classical notions of space and time are not fundamental. When pushed to the Planck scale, they must be replaced. From an observational point of view, the frustrating part is that we cannot see the Planck era directly. The cosmic microwave background shows us the universe when it was already old enough to be transparent. The large-scale structure of galaxies shows us the frozen patterns of perturbations that were amplified later. At best, we can look for delicate fingerprints of Planck-scale physics in the statistics of those patterns. For instance, the tiny fluctuations in the microwave background may retain subtle imprints of how quantum fluctuations behaved during an extremely early phase of rapid expansion, deviations from perfect randomness. Small non-Gaussianities, as cosmologists call them, might one day hint at specific features of the underlying quantum gravity theory. But even in the most optimistic scenarios, we will never obtain a literal image of the Planck era. No telescope will ever photograph it. No detector will ever directly record its events. Its reality, if we can reach it at all, will always be mediated through theories that are tested in indirect ways. This is where the existential dimension returns. For many people, the phrase, "the beginning of the universe," evokes a point of maximum clarity, a definitive moment when everything started, about which there should, in principle, be a simple answer, a yes or no, a single picture. The Planck era tells us almost the opposite. It says that if there is a region that deserves to be called the very earliest phase of the universe, it is precisely the place where our ideas about clarity fail. It is where the questions we are used to asking where, when, what happened first no longer match the structure they are being applied to. We might someday write down equations that describe this domain elegantly. We might learn to speak fluently about pre-geometric states, about emergent time, about quantum histories of space. But even then, the human imagination will be doing something strange. It will be trying to turn a description that does not live natively in time into a story that does. And that translation will always leave something out. From a certain angle, This could feel like defeat. We wanted to know what the universe looked like right after it began. And we end up with talk of Planck scales, quantum foam, emergent geometry. We replace an intuitive picture with abstractions. From another angle, there is a kind of austere beauty here. The universe is telling us that its origin, if that word even applies, is not an event inside a pre-existing container. It is a regime where the container itself and the rules that define events are coming into being in a way that resists compression into a single snapshot. The Planck Era, then, is not just a technical term in cosmology. It is a mirror held up to our need for beginnings. It shows us that the closer we push our theories toward the putative starting line, the more that line dissolves into something that cannot be drawn on a timeline at all. We can continue the story from just beyond that boundary. In a regime where space-time has already emerged enough to be treated as a smooth fabric, where quantum fluctuations can be calculated on a classical background, and where the universe can undergo dramatic, perhaps rapidly accelerating expansion, that is where most cosmological narratives really start, whether they admit it or not, just after the Planck fog has lifted enough for our familiar tools to grip. When that fog thins, what we see is not immediately the gentle, slowly expanding universe of textbook diagrams, but something more abrupt and unsettling, like a breath being drawn in too quickly. Cosmologists use the word inflation for this phase. It sounds economic, and in a way that is not entirely misleading, it is a period during which space itself, instead of growing at a modest pace, may have swelled by an enormous factor in an unimaginably short time. To picture this, imagine you are looking at a balloon that is already somewhat inflated. You watch it grow steadily as air flows in, the way our current universe expands. Inflation is not like that. Inflation is more like a sudden, almost instantaneous surge, where the balloon's size multiplies again and again before you have time to blink. Of course, there is no literal balloon. There is only space, and its own internal scale, which measures distances between any 2 points. During an inflationary phase, that scale does not just increase, it accelerates. Every moment of cosmic time, whatever that meant then, brings a growth that is proportionally larger than the moment before. Why do cosmologists take such a strange idea seriously? Part of the answer lies in what we actually see when we look at the universe today, and in the cosmic microwave background. The universe, on the largest scales we can measure, is astonishingly uniform. The temperature of the microwave background is almost the same in every direction. The density of matter, when averaged over huge regions, is nearly constant. There are small irregularities, the seeds of later structure, but the overall smoothness is striking. At the same time, the geometry of the universe appears very close to what mathematicians call flat. That means that, on vast scales, the rules of geometry resemble those of a flat sheet rather than those of a sphere or a saddle. Triangles drawn across great cosmic distances have angles that add up to almost exactly the familiar value they would have on a flat surface. These two facts create puzzles. The first is often called the horizon problem, though the term can hide its strangeness. A cosmic horizon is like a limit to what regions of space could ever have influenced one another since the beginning. Light can only travel so fast. If two patches of the sky are so far apart that light has not had time to pass between them since the universe began, then, in ordinary thinking, they should not have had any opportunity to coordinate their properties. Yet, when we look at those distant patches, they have almost exactly the same microwave background temperature. It is as though two people on opposite sides of a planet, who have never met, somehow chose the same outfit down to the last detail. The second puzzle is called the flatness problem. In the equations of cosmology, exact flatness is a delicate state. If the density of the universe were even slightly different in the early past, Space would have curved strongly either one way or the other. It would either have collapsed back on itself quickly or expanded so fast that structure never formed. To be as flat as it is now, the early universe would have needed an initial density balanced with extraordinary precision. You can interpret these puzzles in a few ways. One is to say that the universe simply started out very smooth and very finely tuned, for reasons we do not know. Another is to look for a process that would drive it towards smoothness and flatness, even if it began in a more irregular state. Inflation is such a process. The idea, in its simplest form, is that during a very early phase, the energy of the universe was dominated by a field with a strange property. A field, in physics, is something that has a value at every point in space, like temperature or pressure in a room. This particular field, often called the inflaton, would have stored a kind of energy that does not dilute as space expands, at least for a while. When space is filled with this almost constant energy, the equations of general relativity say that it will expand at an accelerating rate. The expansion feeds on itself. Doubling the scale of the universe does not reduce this energy. It simply creates more space filled with the same density of it. The result is an exponential growth. Each little slice of time multiplies the size of the universe by some factor. A key feature of exponential growth is that it can wipe out irregularities. Imagine an old, wrinkled balloon. If you inflate it a little, the wrinkles remain visible. If you inflate it enormously, each wrinkle is stretched so much that, from your limited vantage point on a small part of the surface, it looks almost flat. In the same way, if the universe underwent a period of inflation, any initial lumps or bumps in its geometry would be stretched away. Regions that were once close enough to share information and come to the same temperature would be pushed far apart, so far that they now sit beyond each other's horizons. To observers like us, they look as though they never had contact, yet their properties match because they did, long ago, before inflation separated them. In this story, inflation explains why the microwave background looks so uniform across the sky. The parts of the sky we see on opposite sides were once neighbors in a much smaller pre-inflationary patch, allowed to exchange light and heat until their temperatures matched. Inflation then pulled them apart far faster than light could keep up, freezing in that uniformity across enormous distances. Inflation also explains flatness, at least qualitatively. The rapid expansion drives the curvature of space towards zero, the way stretching the surface of a balloon makes a small patch look flatter and flatter. No matter what the initial curvature was, if inflation lasts long enough, the part of the universe we can see afterward would look almost perfectly flat. So, inflation gives us a smoother universe and an explanation for the delicate balance of its early conditions, without requiring that balance to be built in from the start. It turns what looked like fine-tuning into a dynamical outcome. But there is more. Inflation does not only smooth, it also seeds structure. Quantum fluctuations, the tiny, unavoidable jitters in fields at small scales, would have been present in the inflaton field as well. Normally, such fluctuations are microscopic, meaningless to our macroscopic world. During inflation, however, these fluctuations are stretched along with space. A small ripple in the field's value over a tiny region is pulled out to cosmic scales, becoming a slight variation in the energy density from place to place. Where the density is a little higher, gravity eventually amplifies the difference. Matter falls into these overdense regions more than into others. Over vast amounts of time, they grow into galaxies, clusters, and the cosmic web. In this way, the large-scale structure of the universe becomes a fossil of quantum noise during inflation. The pattern of slightly warmer and cooler spots in the microwave background is then not arbitrary, but a snapshot of these amplified fluctuations when the universe was still very young. After inflation had ended and ordinary expansion had resumed, this picture is strange. But it is not pure fantasy. When cosmologists calculate the statistical properties of these quantum fluctuations in inflationary models, and then compare them with the observed pattern of temperature variations in the microwave background, they find a striking match. The fluctuations are nearly, but not perfectly, scale invariant, which means their strength is almost the same across a wide range of sizes, with only a slight tilt. That is what simple inflation models predict, and it is what the data shows. All of this makes inflation an attractive idea. It smooths, it flattens, it seeds. It ties together several previously disconnected puzzles. And yet, in keeping with the spirit of this whole journey, we have to be careful about how we talk about it. Inflation is not a directly observed event. We do not have a recording of space swelling in that accelerated way. We infer it from patterns that could, in principle, have other explanations. There are alternative scenarios that try to solve the same puzzles with different mechanisms, though inflation remains the leading framework. Even within inflation, there are many models, different choices for the shape of the inflaton's potential energy. The way its energy depends on its value lead to different details. Some versions of inflation may last just long enough to account for the observed smoothness. Others naturally produce an ever-branching multiverse, in which inflation continues in some regions while stopping in others, creating bubble universes with varying properties. Most of inflation, if it happened, is permanently hidden from us. The part of the universe we can see is a tiny patch of the region that emerged from inflation. The rest lies beyond our cosmic horizon, causally disconnected. Any initial irregularities on ultra-large scales may have been stretched so far that no observer inside any one bubble universe could ever see them. This means that inflation is, by design, somewhat self-concealing. It explains why we observe what we do. But the process that created that observable patch is only partly reconstructible. The vast majority of the inflating region, if it existed, is forever outside our reach. From an existential point of view, this does something subtle to the question, what was the universe like right after it began? It's one star. If inflation is correct, then by the time the universe becomes describable in the ways we have been using, by the time we can talk about a hot plasma, about light decoupling, about atoms forming the initial violent growth, has already happened. The chaotic, pre-inflationary conditions, and the Planck Era before that, are smeared out beyond recognition. The earliest universe we can meaningfully describe might therefore not be the absolute beginning, but the end of inflation, a moment when space has become smooth enough, and time has become regular enough, that our familiar equations apply. From then on, the story becomes less exotic. The inflaton field decays, dumping its energy into radiation and matter in a process often called reheating. The universe becomes a dense, hot soup of particles. Expansion continues, but at a gentler rate, governed by the balance between radiation, matter, and later dark energy. In this post-inflationary phase, the universe looks more like the one we are used to hearing about, cooling, expanding, gradually forming structures as gravity amplifies tiny differences. It is a universe we can simulate in computers, test in particle accelerators, and cross-check with astronomical observations. But the threshold we just crossed, the ending of inflation, the transition from wild acceleration to ordinary expansion, is also a kind of horizon. Not an observational horizon this time, but a conceptual one. On one side of it lies a domain where quantum gravity, emergent geometry, and unknown physics dominate. On the other side lies a domain where classical space-time is a good approximation, and quantum behavior can be treated as fluctuations on a stable background. When we say after the threshold, we are admitting that our honest narrative about the early universe begins only there. Whatever lies earlier, whatever the Planck Era truly was, and whatever pre-inflationary conditions might have existed are not part of our reliable story. So when someone asks what the universe looked like right after it began, there are at least two different answers, depending on how much honesty we are willing to carry. In a simplified, popular account, we might point to the hot, dense plasma shortly after inflation, when the universe was filled with radiation, particles, and a uniform glow, and say, it looked like that. In a more careful account, we would say, the earliest phase we can describe with some confidence is already after a brief, explosive inflationary expansion that smoothed out previous irregularities. What the universe was like before that is wrapped up with quantum gravity and emergent space-time, and we do not have a complete language for it. Inflation, in this sense, is not the beginning. It is the first chapter whose text we can partly read. The pages before it are damaged, written in a script we have not fully decoded. This is not a failure of cosmology. It is its most honest achievement. We can trace the universe back through its cooling, through the formation of atoms, through the release of the cosmic microwave background, through the dominance of radiation, back to the end of inflation. At that threshold, the equations start to lose their footing, and we mark the boundary with Planck units and speculation. Beyond that, we can only say that, if there was a beginning, it did not look like anything we can picture. It did not unfold inside a quiet pre-existing time, whatever right after it began truly means. Inflation and the smoother universe that follows are already the aftermath, not the spark. If what we call the beginning is already aftermath, then the old question creeps back in a new form: aftermath of what? It is here that cosmology steps beyond the ground of tested models and into a landscape of competing stories. Not stories in the sense of fictions, but in the sense of carefully built possibilities that reach further than our current evidence can go. Each one tries, in its own way, to answer a question that may not have a single, clean answer. What, if anything, came before the hot, expanding universe we see? One family of ideas imagines that our universe is part of a cycle. Expansion is not the entire story, it is a phase between others. In these cyclic or bouncing models, the universe might have gone through earlier periods of contraction, shrinking under its own gravity, before some new physics intervened and turned collapse into a rebound. The Big Bang, in this kind of picture, is not a creation from nothing, but a bounce from a previous state. The details vary. In some versions, a previous universe looks much like ours, only running backward in time, contracting instead of expanding. In others, the contracting phase is very different in character, perhaps dominated by smooth fields that erase memory of what came before. At the moment of highest density, when classical gravity would predict a singularity, quantum gravity effects could become dominant and prevent an actual breakdown, steering the universe into re-expansion. A bounce is intuitively appealing. It preserves a sense of continuity. There is always a before. The universe does not begin. It oscillates. But this is still largely speculative. To make such a picture precise, we need a concrete theory of quantum gravity that shows, in detail, how the bounce works and under what conditions it occurs. Some approaches to quantum gravity, especially loop quantum cosmology, do suggest mechanisms by which a big crunch can turn into a big bang. In these scenarios, the geometry of space has a built-in discreteness that prevents infinite compression. Instead of a singularity, you get a minimum volume and then re-expansion. These models are mathematically interesting, and they address the singularity problem elegantly. Yet the observational signatures that might distinguish a bounce from a simple beginning are subtle. They might show up as delicate deviations from the simplest inflationary predictions in the cosmic microwave background, or as specific patterns in primordial gravitational waves. the ripples in space-time created in the early universe. So far, no clear, decisive evidence has appeared. Another set of ideas reaches further still, suggesting that what we call our universe is only one region in a larger reality. In some versions of eternal inflation, the inflating state of space does not end everywhere at once. Patches of the inflating region can stop inflating and form bubble universes like ours, where expansion slows and structure can form. But other patches keep inflating, spawning more bubbles without end. This can lead to a multiverse, an endless, branching structure of regions, each with its own emergent space and time, perhaps with different physical constants. From inside one bubble, observers see a Big Bang and a subsequent evolution. But from the imagined outside vantage, there is no single beginning, only an ongoing process of bubble formation. There is no global time at which the whole thing starts. This picture shifts the question in a particular way. Instead of asking, what came before our universe? It invites, what is the larger process that gives rise to multiple universes, including ours? The beginning, if there is one, may belong to that deeper process, not to any one bubble. The multiverse idea is controversial. It arises naturally in many inflationary models and in some versions of string theory, but it is difficult to test directly. By construction, other bubble universes are causally disconnected from us. Their light, if they have light in anything like our sense, can never reach us. Some physicists argue that indirect tests are possible through statistical reasoning. If the multiverse generates many universes with different properties, perhaps we can explain why we live in one that appears finely tuned for complex structures and life. We should not be surprised to find ourselves in a universe where conditions allow observers, because only in such universes can this question be asked. Others worry that without clear observational anchors, multiverse reasoning drifts too close to metaphysics. If every possible outcome happens somewhere, what does it mean to confirm a prediction? At what point does a scientific model become indistinguishable from a philosophical one? There are quieter proposals as well, ones that do not multiply universes but reshape the nature of time. The so-called no-boundary idea, associated with the work of Stephen Hawking and James Hartle, is one example. Here, the universe does not begin from a sharp singularity, but from a kind of rounded-off geometry. In this picture, if you go back toward the earliest times, the distinction between time and space gradually fades. Near the origin, time behaves more like a spatial direction. There is no edge in time. Just as there is no edge at the North Pole on a globe, the singular beginning is replaced by a smooth cap. The word no boundary refers to this smoothness. It suggests that the universe is finite in a certain mathematical sense, but does not have a boundary in need of external conditions. There is no earlier time where something outside the universe must make a choice. Explaining this fully requires tools from quantum cosmology, where the whole universe is treated as a quantum object described by something like a wave function. In that setting, the no-boundary condition is a particular way of specifying how that wave function behaves at small scales. It is not an image of a literal pre-time realm, but a technical prescription that replaces the singularity with a region where Euclidean geometry without a time direction, dominates. Roger Penrose's conformal cyclic cosmology offers a different twist on cycles. Instead of bouncing through a dense phase, his idea links the far future of one cosmic epoch to the Big Bang of the next through a mathematical transformation. The key ingredient is conformal geometry, which preserves angles but not absolute sizes. In such a description, the distinction between very large and very small can, in some circumstances, be smoothed away. Penrose's proposal is that the remote future of our universe, after all, matter has decayed and only very low-energy radiation remains, can be reinterpreted via a conformal rescaling as the beginning of a new universe. In that view, our Big Bang is the continuation, under a different geometric guise, of a previous cosmic era's long, thin tail. There is no singular crunch or bounce, just a relabeling of what counts as large and small, which ties one epoch to the next. This is mathematically elegant, but again, highly speculative. Penrose and collaborators have claimed possible evidence in the form of certain circular patterns in the cosmic microwave background, which they interpret as echoes of events from a previous cycle. Most cosmologists are unconvinced. The data can be explained without invoking such cycles, and the statistical significance of the claimed patterns is debated. There are also emergent universe scenarios. In these, the universe does not begin from a singularity or a bounce, but emerges gradually from a more static or slowly changing state. For a very long time in the past, the cosmos might have existed in a quiescent configuration, perhaps dominated by some form of vacuum energy. Then, under the right conditions, a transition occurs that ignites a hot, expanding phase like ours. In such models, the question of what came before is answered by pointing to that pre-emergent state. But then we must ask, what sustains that state? And what triggers the transition? The mystery is not eliminated, only moved. Across all these ideas, one pattern stands out. The universe does not easily give us a single, the satisfying answer to the question of what came before its hot beginning. Our best tested theories point to a boundary, a domain where the language of space, time, and cause no longer works as we expect. Beyond that, we encounter a branching tree of possibilities, guided by different intuitions about how to tame singularities and how to merge quantum rules with gravity. Some of these possibilities preserve an infinite past. Some replace the beginning with a bounce. Some link cycles in subtle geometric ways. Some suggest a larger multiverse in which beginnings are local, not global. From the perspective of meaning, it is tempting to ask which, if any, is true. But part of the honesty we have been circling around is this: our current observations do not single out a unique story. They strongly favor the broad outlines of a hot, expanding early universe, with inflation or something like it, smoothing and seeding structure. They point firmly to a time when the cosmos was very different from what we see now. They do not, yet, tell us whether that hot phase had a before in any sense that our minds can comfortably inhabit. We can rank these models by internal consistency, by how naturally they arise from known physics, by how clearly they connect to potential observations. We can prefer some on aesthetic grounds, or on the basis of how they handle deep issues like entropy and information. But in the quiet truth of late-night cosmology, we have to admit that the question, what really came before, remains open. And perhaps more importantly, we have to admit that even if a future theory answers it, the answer may not feel like the closure we imagine. If we discover that the Big Bang was a bounce from a previous collapse, we will then ask, why that cycle? Why those laws? Why any universe at all? If we find strong support for a multiverse, we will ask, why this branch? Why this pattern of vacuum energies? Why this particular chain of inflating and cooling regions? If quantum cosmology gives us a no-boundary wave function from which our universe arises with some probability, we will ask, why that wave function? Why those boundary conditions? The search for a cosmic origin keeps retreating into deeper layers of description. Each time we peel one back, we uncover a more abstract question behind it. For some, this is frustrating. We want the universe to have a point, a clear first step that explains everything after it. We want a beginning that behaves like the opening line of a book. Once you see it, the rest falls into place. Cosmology, at its most honest, offers something quieter and stranger. It shows us that what we call the beginning is not a single frame to be recovered, but a boundary where our stories meet their own limits. Space and time, the stage on which our lives unfold, do not extend indefinitely backward with the same character. They bend, thin, and finally dissolve into structures that resist being narrated at all. We can say, with justified confidence, that the universe was once hotter, denser, and smoother than it is now. We can say that light, long before it streamed to us from galaxies, struggled to move through an opaque plasma. We can say that the afterglow of that hot phase still bathes us, and that its pattern encodes clues to processes near the edge of our understanding. We can also say that, as we push toward that edge, our language fails before the universe does. The cosmos continues, in some form, on the other side of our concepts. It may be cyclic, branching, emergent, or something we have not yet imagined. Whatever it is, it does not fit neatly into the human habits of before and after, cause and effect, beginning and end. So perhaps the most honest way to answer the question, what was the Big Bang, and what did the universe look like right after it began, is to turn it gently. The Big Bang, as far as our best science can now see, is not a fireball exploding into emptiness. It is a hot, dense early phase of an expanding space-time. A phase whose traces remain in the background radiation and in the large-scale structure of galaxies. It is also a boundary in our theories, a marker of where general relativity and quantum mechanics, as we currently understand them, stop cooperating. What the universe looked like right after that boundary is not a picture we can draw. It is a set of physical conditions we can partly describe: extreme temperature, high density, rapid expansion, matter and radiation tangled. Before that, in the Planck Era and beyond, we step into a regime where questions about appearance give way to questions about the meaning of space and time themselves. And meaning, the kind we usually hunger for, is not waiting there like a prize. It is something we construct now, as beings who find themselves very late in this story, on a small planet around an ordinary star, under a sky filled with light that has traveled a very long way. We do not live at the beginning of the universe. We live in its wake. Our task is not to stand outside it and watch its birth, but to recognize that whatever that birth was, it made possible this moment, a mind wondering how far understanding can reach before it has to say, softly, that beyond this point, the universe continues without us. That admission is not a defeat, it is a way of aligning ourselves with the truth that cosmology, at its most humble, keeps revealing. The origin of the universe is not a problem to be solved once and for all, but a horizon that recedes as our knowledge grows, reminding us, again and again, that we are finite creatures thinking inside a vast and indifferent, yet astonishingly intelligible, whole.